There is a truth that most people never realize. While you are resting, there are companies spending billions of dollars to turn Mars into a place where humans can live. Elon Musk has said that his goal is to make humanity a multiplanetary species. And according to some of the most recent plans, the first human missions to Mars could happen within this decade. It sounds like the future is very close. But there is a problem that most of these conversations never mention. It's not technology, it's not rockets, and it's not money. It's something far simpler and much harder to change. The human body. Because when you leave Earth, you are not just entering space. You are stepping out of a physical system that has shaped and sustained you for millions of years. And based on what science understands as of 2026, there is a very real possibility that that journey may not have a way back. And now we begin with a simple question. What if the greatest dream of humanity is working against the very way our bodies were designed? Now, let's begin. When humans look up at the night sky, Mars has always been one of the most distinctive points of light. Not because it is the largest planet, not because it is the closest, but because of its color. A deep red that makes it stand out, almost alive against the silent darkness of space. For centuries, that red color has sparked imagination. In the late 19th century, when astronomers first observed Mars through telescopes, theories began to emerge about canals, possible signs of a civilization. Although later proven to be optical illusions, the idea that Mars was somehow like Earth had already taken root. Then, in 1965, the Mariner 4 probe flew past Mars and sent back the first close-up images. There were no canals, no oceans, only a dry, cratered surface. But what's interesting is, the dream didn't end there. It simply changed form. Mars, in a way, has never been just a planet. It has always been a possibility. A version of Earth, somewhere else. A place humanity might go if one day this planet is no longer enough. That idea carried on through generations, and by the 2000s, as rovers like Spirit, Opportunity, and later Curiosity began exploring the Martian surface, the images they sent back created a strange sense of familiarity once again. Vast rocky plains, towering mountains, valleys stretching for hundreds of kilometers. Even Olympus Mons, the largest volcano in the solar system, rises about 22 kilometers high, nearly 3 times the height of Mount Everest. If you looked only at the terrain, it would not be hard to mistake some of these landscapes for a desert on Earth. And that familiarity is where the misunderstanding begins. Because when something looks like Earth, we tend to believe it behaves like Earth. But physics doesn't care about familiarity, it only responds to conditions. And when you place these two planets side by side, the differences are no longer minor details, they are fundamental. The average distance between Earth and Mars is about 225 million kilometers. At their closest, that distance drops to around 55 million kilometers. But this alignment only occurs roughly every 26 months. That means every mission to Mars is tied to a very specific launch window. Miss it, and you may have to wait more than 2 years. From the very beginning, this is not a flexible journey. And once you leave Earth, you enter an environment where every number begins to change. On Earth, gravity is about 9.8 meters per second squared. You don't think about it, but your entire body depends on it every second. On Mars, that number drops to about 3.7 meters per second squared. In other words, if you weigh 70 kilograms on Earth, you would only feel about 26 to 27 kilograms on Mars. It sounds lighter, but for the body, this is not relief. It is a change in environment. Your bones are built to carry load. Your muscles exist to resist gravity. When that force is reduced by nearly 2/3, your body no longer has a reason to maintain its original structure. And this change doesn't take decades. Studies on the International Space Station show that after just 4 to 6 weeks in microgravity, the human body already begins to lose bone density and muscle mass. Mars is not zero gravity, but it is low enough to create similar long-term effects. Next comes the atmosphere. On Earth, the average atmospheric pressure is about 101.3 kilopascals. This pressure allows water to remain stable in liquid form, keeps your blood functioning normally, and supports natural breathing. On Mars, surface pressure is only about 0.6 to 0.7 kilopascals, less than 1% of Earth's. This creates a direct consequence. At that pressure, liquid water is almost impossible to sustain. It either freezes or turns directly into vapor in a process called sublimation. And if water is unstable, then one of the fundamental requirements for life is unstable as well. The atmosphere itself doesn't help. About 95% of it is carbon dioxide. Oxygen exists only in trace amounts, not enough to sustain human life. Which means every breath you take must be carried with you or artificially produced. There is no natural support from the environment. Then comes temperature. On Earth, the average global temperature is around 15 degrees Celsius. On Mars, it's about minus 63 degrees Celsius. But the key issue is not the average, it's the fluctuation. At the Martian equator, temperatures can reach around 20 degrees Celsius during the day under ideal conditions. But just hours later, after sunset, they can drop below minus 80 degrees Celsius. Such rapid and extreme shifts are far beyond what the human body is designed to handle directly. And even all of this is still not the biggest limitation, because there is something else on Mars, something you cannot see, cannot feel immediately, but that affects you at the deepest level: radiation. Earth is protected by a strong magnetic field that deflects most high-energy particles from the sun and deep space. Its thick atmosphere absorbs much of what remains. Mars has neither of these protections at a global scale. Its magnetic field is almost non-existent, and its atmosphere is too thin to provide meaningful shielding. Data from exploration missions show that radiation levels on the surface of Mars average about 0.2 to 0.3 millisieverts per day. Over a year, that adds up to around 70 to 100 millisieverts. For comparison, a person on Earth typically receives about 2 to 3 millisieverts per year from natural sources. This is not a small difference, it is an order of magnitude. And when you bring all of these factors together, a clearer picture begins to form. It's not that Mars is missing a few conditions to become Earth, it's that Mars operates under an entirely different set of conditions. Conditions the human body was never designed to live in long term. What's important is that none of this is new information. It has been confirmed over decades of research through robotic missions and long-term simulations. Yet the way we talk about Mars in everyday life is often much simpler. We talk about building bases, growing plants, creating a new society. And those ideas are not wrong, but they often skip a more fundamental question. Not what we can build on Mars, but how far the human body can adapt before it begins to change in ways that cannot be reversed. And when that question is asked seriously, the story of Mars stops being just a story of exploration. It becomes a test of our limits. When the spacecraft leaves Earth, nothing changes immediately. There is no clear moment when you realize you've just entered a completely different environment. No sudden shock strong enough to make you stop and think. Just a very subtle shift, almost unnoticeable in the first few minutes. Gravity begins to fade. Your body is no longer pulled downward. You no longer feel the familiar weight of yourself. If you let go of something, it doesn't fall. It simply floats. At first, that feeling can be fascinating, a kind of freedom that has never existed on Earth. But the human body was not designed to understand freedom in that way. Within minutes, something else begins to emerge. Blood in your body, which has always been pulled downward by gravity, no longer has a reason to stay there. It starts shifting upward, concentrating more in your head and chest. Your face may feel slightly tighter. Some describe it as a sensation similar to hanging upside down, except this time it doesn't end. Your vestibular system, the inner ear mechanism that helps you maintain balance, begins to lose its familiar reference point. There is no longer a clear up or down in the way you once understood. You turn your head, but you're not quite sure which direction you're rotating. You move, but it no longer feels like walking. During the first few days, about 60 to 70% of astronauts experience space motion sickness, nausea, disorientation, a strange feeling that your body no longer belongs entirely to you. But then, after a few days, your body begins to adapt. Or more accurately, it begins to change. After about a week, the discomfort starts to fade. You learn to move by gently pushing against the walls of the spacecraft instead of walking. You no longer need to maintain balance. Movement becomes simpler. And it is this simplicity that creates an illusion that everything is fine, that this is just another environment, not a problem. But while you are getting used to this new state, something else slowly becomes more noticeable. Distance. At first, distance is not something you feel directly. You can still communicate with Earth. Signals still reach you. Everything seems connected. But over time, that connection begins to change. At its closest, Earth and Mars are about 55 million kilometers apart. But most of the time, that distance is over 200 million kilometers, and when the two planets are on opposite sides of the Sun, it can exceed 400 million kilometers. This is no longer a distance the human mind can easily comprehend. Light, traveling at about 300,000 kilometers per second, takes anywhere from 3 to over 20 minutes to travel between Mars and Earth, which means every message you send will always be delayed. There are no real-time conversations, no immediate responses. A question is sent, and you wait. Not seconds, but long minutes, just to receive a reply. And this is not a new problem. Since the 1960s, when early missions like Mariner approached Mars, engineers had to design systems that were almost entirely autonomous. Not because they wanted to, but because they had no choice. By 1997, with Mars Pathfinder, and later in 2004 with Spirit and Opportunity, robotic missions began operating on the Martian surface for extended periods. But even then, every command had to be calculated in advance. There was no real-time control, no instant reaction. By 2012, Curiosity landed with more advanced instruments, capable of analyzing soil and atmosphere. And in 2021, Perseverance continued the mission, even testing oxygen production directly from the Martian atmosphere using the MOXIE device. This was a significant step, because if humans are ever going to survive there, they cannot bring everything from Earth. They have to learn how to create what they need, on site. But going from a small device on a robotic rover to a system large enough to sustain human life for years is an entirely different challenge. Not just in engineering, but in reliability. Because in that environment, there is no margin for error. And while all of this is happening, you are still on that spacecraft, moving farther and farther away from Earth, inside a closed environment where everything is controlled, but nothing is natural. After a few weeks, you may begin to notice something else. Your body doesn't just feel lighter without gravity. It starts to feel unfamiliar in a deeper way. You don't need effort to stand, no need to balance, no need to resist any force pulling you down. Everything becomes easier, in a way that feels almost suspicious, and your body, in its own way, begins to respond. Familiar movements lose their feedback. You no longer feel the pressure of the ground. You no longer feel your own weight. Sleep begins to change. In orbit, a full cycle can last only about 90 minutes, with 16 sunrises and sunsets every 24 hours. Even though the spacecraft tries to simulate a day-night cycle, your body still senses the difference. You sleep, but not as deeply. You wake up, but not fully refreshed. Not because you aren't tired, but because your body is no longer receiving the signals it relies on to regulate its rhythm. And then there is another shift, more subtle, your sense of space. On Earth, you always know where you are. You know what is floor, what is ceiling. You have a clear relationship with your surroundings. In space, that relationship becomes fluid. You can rotate without realizing it. You can remain upside down for long periods without feeling anything unusual. At first, it can feel interesting, but over time, it creates a strange sensation, as if you no longer fully belong to any direction. And in the quiet moments, when there is no work, no conversation, nothing but the steady hum of the spacecraft systems, a thought may begin to appear. You are very far from Earth. There is no blue sky, no natural air, none of the things you once took for granted. Only a closed space and the vast emptiness beyond it. In long-duration simulations on Earth, where crews live in isolation for hundreds of days to prepare for Mars missions, one of the most difficult challenges is not the workload, it is monotony. Everything repeats. No change in scenery, no new stimulation, no sense of escape. And while your body is slowly changing, the environment offers no natural support. No plants, no sunlight in the way you once felt it. No living system around you responding to your presence. At this stage, you might still believe that you are adapting. Everything is still functioning. You are still alive, still moving, still completing your tasks. But the truth is, this adaptation is not a stable balance. It is a transition whose endpoint you cannot yet see. And that is where everything begins to change. Because what you are experiencing is only the surface. The real changes are happening much deeper. And once we begin to look at those changes, the picture will become much clearer. If there is one thing in this journey that you cannot see, but that affects you more than anything else, it is radiation. No sound, no color, no clear sign that tells you it is there. And yet, it is always there. And unlike the changes you can feel in your body, radiation does not wait for you to notice it. It begins affecting you the moment you leave Earth. On this planet, you almost never think about radiation. Not because it doesn't exist, but because you are protected from most of it. Earth has a strong magnetic field, creating an invisible shield that deflects high-energy particles coming from the sun and deep space. Above you, a thick atmosphere absorbs much of what remains. As a result, an average person on Earth is exposed to only about 2 to 3 millisieverts of radiation per year from natural sources. It is a small number, one the body can handle without significant short-term effects. But when you leave that protective system, everything changes. In deep space, there is no magnetic field strong enough to shield you, no thick atmosphere to absorb incoming energy. You are almost directly exposed to some of the most intense radiation sources in the solar system. Scientists generally divide space radiation into two main types. The first is solar radiation, especially during events known as solar particle events, when the sun releases powerful streams of high-energy particles. The second is galactic cosmic rays. These are extremely high-energy particles originating from distant events such as supernovae, traveling through space for vast periods of time before reaching our solar system. You cannot avoid them. You cannot see them. And for most of the time, you won't even know they are passing through your body. Based on data collected from spacecraft instruments and Mars-related missions, the total radiation dose an astronaut might receive during a round-trip journey lasting about 2 to 3 years is estimated to be between 0.6 and 1 sievert. This is not an easy number to visualize, but to put it into perspective, a full-body CT scan typically exposes you to about 10 millisieverts, which means a Mars mission could expose you to the equivalent of dozens, even hundreds of such scans. On Earth, exposure at around 1 sievert is known to significantly increase lifetime cancer risk. But the issue is not only long-term risk. What concerns scientists even more is how radiation affects the body over time. Unlike an injury you can immediately feel, radiation operates at the cellular level. It can damage DNA. It can alter how cells divide, and in some cases, it can create changes that the body cannot fully repair. This becomes especially important when it comes to sensitive organs like the brain. In animal studies and simulation models, researchers have observed that cosmic radiation may affect cognitive function, reducing memory, slowing processing speed, and impairing decision-making. These effects do not happen in a day or a week. They accumulate, slowly, but continuously. And in a journey that lasts for years, that accumulation becomes impossible to ignore. The next question is protection. If radiation is dangerous, the natural response is to shield against it. But in space, this is not as simple as it is on Earth. To block high-energy particles, you need thick materials. But the thicker the material, the heavier it becomes. And in space missions, every kilogram matters. In some cases, when high-energy particles collide with shielding materials, they can even produce secondary radiation, making the problem more complex rather than simpler. This is why designing an effective radiation protection system remains an unsolved challenge. Organizations like NASA have explored many different approaches, from using water as a natural shielding layer to designing dedicated shelter areas inside spacecraft where astronauts can retreat during periods of intense radiation. But all of these solutions have limits. They can reduce risk, but they cannot eliminate it. And importantly, even after you land on Mars, the problem does not go away. The surface of Mars lacks a global magnetic field strong enough to protect you. Its atmosphere is too thin to provide effective shielding. Radiation levels on the Martian surface are estimated at around 0.2 to 0.3 millisieverts per day. Over the course of a year, that adds up to roughly 70 to 100 millisieverts, many times higher than the average exposure on Earth. This means that even after completing the long journey to get there, the environment you arrive in continues to apply pressure to your body every single day. There is no pause, no natural safe zone, only artificial solutions and their limitations. At this point, something becomes clearer. What you felt earlier, the lightness, the disorientation, the changes in sensation, those were only the surface. Radiation does not create immediate sensations, but it is one of the forces that shapes the final outcome of the journey. You can adapt to moving in low gravity. You can learn to live in a confined space. You can accept isolation. But you cannot learn how to prevent your body from being affected by radiation. This is not a skill. It is a biological limit. And when that limit is placed within a journey that lasts for years, it becomes one of the most critical factors to consider. Not something that causes problems immediately, but something that ensures problems will appear over time. And that is where the story begins to shift into a new phase. Because if what you've experienced so far is only the surface, and radiation is the invisible pressure, then the next question becomes, what is really happening inside your body when all of these factors come together? And once that question is asked, everything begins to become clearer. Because what is happening inside your body does not exist in isolation. It does not unfold in a neutral space. It unfolds within an environment where every surrounding factor is adding pressure. An environment that not only lacks the conditions necessary for life, but continuously makes everything more difficult over time. That environment is the surface of Mars. From a distance, the planet appears quiet. No oceans, no complex ecosystems, no visible movement like on Earth. But that silence does not mean safety. It simply means there is nothing there to support you. One of the most defining features of Mars is its dust storms. On Earth, storms usually last hours, sometimes days, rarely more than a week. On Mars, dust storms can last for months, and in some cases, spread across nearly the entire planet. Observations from orbital missions show that these storms can stretch across thousands of kilometers, blocking sunlight for extended periods. This does not only affect visibility, it directly affects energy. If you rely on solar power, your energy output can drop significantly during these periods. And in an environment where every system depends on energy to sustain life, this is not a minor detail. Temperature is also unstable in a way we are not used to. On Mars, the difference between day and night temperatures can reach 80 to 100 degrees Celsius. A location may feel relatively warm during the day, but within just a few hours, temperatures can fall to levels that place extreme stress on any material. This creates a constant demand on protective systems. You don't just need a sealed environment, you need one that can remain stable in conditions where everything outside is constantly shifting. And then there is the surface itself. Martian soil is not like soil on Earth. It contains compounds such as perchlorates, chemicals that can be toxic to humans with prolonged exposure. This means that even if you think about growing food, you cannot simply use the natural soil without processing it first. Everything must be controlled. Everything must be filtered. Nothing from the environment can be used directly without risk. The same applies to the air. As mentioned earlier, the Martian atmosphere is mostly carbon dioxide with extremely low pressure. But more importantly, you cannot simply step outside for a moment the way you can on Earth. There is no concept of going outside for fresh air, no transition space. Between the environment you live in and the one outside, there is an absolute boundary. And every time you cross that boundary, you depend entirely on your life support system. Here, there are no small mistakes. A system failure is not an inconvenience. It is an emergency. And in many cases, there is no immediate fix. The distance we discussed earlier does not just affect communication, it affects support. On Earth, if a critical system fails, you can call for help, replace components, or receive assistance from outside. On Mars, you are your own support system. Everything you need must already be there. And if a critical component fails without a backup, you cannot wait for a solution from Earth within a short time. Even robotic missions have shown just how unforgiving this environment is. One example is the Opportunity rover, which operated on Mars from 2004 to 2018. It lasted far longer than expected, but eventually a global dust storm reduced its energy levels to the point where it could no longer function. Not because of a major failure, but because the environment simply no longer allowed it to continue. And that was a machine. No biological needs, no need for air, no requirement for stable human temperatures. When you place humans into that same environment, the demands become far greater. You don't just need energy. You need breathable air, clean water, stable pressure, controlled temperature, and a system capable of maintaining all of this continuously, without interruption, for years. There is no pause. There is no moment when you can shut things down and let the natural environment take over. Everything must keep running all the time. And when you combine this with what is happening inside your body, something begins to become clearer. You are not just adapting to a new environment, you are constantly resisting it. Every breath, every movement, every hour you exist depends on an artificial system working exactly as expected. No deviation, no margin. And in a journey that lasts for years, that dependence does not decrease, it increases. This is not an environment you can simply get used to. This is an environment where you must maintain an artificial state of stability, while everything outside is constantly pulling you away from it. And that is where the question begins to shift once again. It is no longer about whether you can live on Mars. It becomes how long you can maintain that state before something, no matter how small, begins to break the balance. If you look at it from a distance, many people assume that the Mars problem is simply a matter of distance. Earth is here, Mars is there. Build a powerful enough rocket and you go. When you want to return, you just fly back. At first glance, that feels like a very natural way to think. But what space agencies have understood for decades reveals something very different. The greatest challenge of a Mars mission is not leaving Earth. It is the structure of the trajectory, the energy required, and the timing of the entire journey. A favorable launch window from Earth to Mars appears only about once every 26 months. If you miss it, the entire plan may need to be delayed by more than 2 years. Even NASA has emphasized that the relative positions of the two planets are only most favorable for a few weeks within each 26-month cycle. That number might sound like just a technical detail, but in reality, it completely changes the nature of the mission. Because it means you cannot treat Mars like a long trip. You cannot arrive there and then decide to return a few weeks earlier, or a few months earlier. In most energy-efficient mission architectures studied over decades, a crewed Mars mission follows what is known as a conjunction class trajectory. You travel to Mars using a low-energy path, remain on or around Mars for a long period of time, and only return when the two planets once again align properly. These mission profiles typically assume about 500 days on Mars and a total mission duration of around 900 days or more. In other words, this is not a one-year journey. It is closer to an entire phase of your life. A low-energy mission does not just require months to reach Mars. It requires accepting from the very beginning that you cannot return whenever you want. The outbound cruise alone is often described as around 200 days, nearly 7 months. And that is only the first part. This is where the nature of the story begins to change. Up to now, we have talked about the body, about radiation, about an environment that offers no pause. But here, everything must be viewed through a different layer: time. Because if the environment gives you no rest, then the orbit gives you no choice. Even before humans set foot on Mars, robotic missions had already revealed how strict this timing problem is. Opportunity took about 6 months to arrive. Curiosity also required many months. Today, NASA still describes the cruise phase to Mars as roughly 200 days. This is not a journey you can shorten at will, not if you want to keep energy requirements within realistic limits. And that is only the journey there. The real challenge begins once you arrive. If a crew lands on Mars using a conjunction class trajectory, they are not simply staying for research. They are locked into the orbital mechanics of two moving planets. Earth does not wait for them. Mars does not wait either. Both continue orbiting the Sun at their own speeds. And because of that, the way back only opens when the geometry allows it. This has been studied in mission designs for decades, and the conclusion has remained consistent. To reduce energy requirements and keep payloads manageable, you must accept a long stay. At this point, a very reasonable question arises. Why not choose a different trajectory? Why not use more energy to return earlier? Why not design a shorter mission? The answer is simple, but not easy. You can, but the cost rises dramatically. Shorter missions, often called opposition class, have been studied for a long time, but they typically require one of two things: either significantly higher energy or propulsion technologies far beyond what is currently standard for human missions. They do not remove the problem, they move it. More mass, more systems, more risk, or technology that is not yet ready at a human-rated level. That is why NASA and many research groups still consider conjunction-class missions the most practical option. So when we say the real challenge is that you cannot come back when you want, that is not an exaggeration. It is the nature of the problem. A crew going to Mars is not stepping into an expedition. They are stepping into a timeline that has already been locked in. If something goes wrong psychologically after 3 months on the surface, there is no option to bring them home immediately. If a crew member can no longer tolerate confinement after 200 days, there is no emergency return flight waiting. If a system begins to degrade, there is no way to call for help and have engineers arrive in a few days. In low Earth orbit, humans have always had a quiet form of reassurance. Earth is still close. The International Space Station is only a few hundred kilometers away. Even though it is dangerous, it exists within a system of rescue and resupply that has been built over decades. Cargo arrives multiple times a year. People go up and come back down. There is still a logistical chain. Mars has none of that. When you move from low Earth orbit to Mars, what humanity truly loses is not just physical distance. It is the ability to change its mind. And in a very quiet way, that changes everything. A person can accept risk if they know they can still turn back. A person can endure isolation if they know it has a clear end. But when a mission is designed as a multi-year commitment with no early exit, the psychology shifts. It is no longer, I will go and I will try. It becomes, I will go and I will remain there until the orbit allows me to leave. On paper, this difference may seem small. In reality, it is the difference between exploration and commitment. Mission planners understand this very well. That is why, in many NASA documents, work structures, behavioral planning, surface schedules, and crew roles are designed for very long durations. They are not planning for weeks, they are planning for hundreds of days, after months of travel and before months of return. That shows how serious the problem is. But it also reveals something else. Science is not naive about Mars. The people working in this field do not confuse it with a romantic adventure. For more than half a century, from early Mars reference missions to modern designs, they have always returned to the same constraint. Time to go, time to wait, time to come back. And everything that must be sustained throughout that entire period. Because once you accept a mission lasting around 900 to 1,000 days, every other problem grows with it. You need more food, more water, more spare parts, more redundancy, more psychological stability, more ability to repair things yourself. And most importantly, you need a body strong enough to endure all of it, without failing before the moment you are allowed to return. Earlier, we said that change does not happen suddenly, that radiation does not need you to notice it to begin working, that Mars offers no pause. Now, when you add time to the equation, all of that pressure begins to stack. It is no longer 6 or 7 months in space. It is no longer a harsh planet. It is no longer an isolated environment. It is all of those things, lasting for years. And this is where another dimension of the problem appears. You do not just need to survive long enough to return. You need to remain stable enough for returning to still matter. An orbital window may open after hundreds of days. But if by then your body has weakened too much, if your cardiovascular system has changed, if your bones and muscles have degraded, if your nervous system has been under prolonged stress, then having a way back no longer means you can return to the life you once had. This is a point worth pausing on. Humans often think of returning as a physical act, going back to a location in space. But for Mars missions, returning also means returning to Earth's conditions, returning to 1G gravity, returning to natural biological rhythms, returning to an environment your body may have been away from for too long. So the way back is not just orbital. It is the intersection of orbit, time, and biology. Robotic missions help us understand Mars. Mission models help us understand time and energy. Human research in space helps us understand the cost. And when you put all three together, you begin to see why Mars is fundamentally different from the Moon. With the Moon, Apollo missions operated on a timescale humans can still grasp. A few days to go, a short stay, a few days to return. If something went wrong, Earth was still conceptually near. Mars operates on a completely different scale, a scale where every decision must hold for months, and every mistake must be endured for a long time before it can be corrected. Perhaps that is what makes Mars feel so strange in the human mind. It is close enough to dream about, but far enough that it does not forgive simplification. It is where imagination reaches forward, and where physics forces us to be honest. You can tell a powerful story about landing there. You can design beautiful visions of bases, cities, greenhouses, and launch pads. You can speak about a multi-planetary future. But beneath all of that, the problem remains. Launch windows still open on a fixed cycle. The journey still takes months. Long stays are still the most practical solution, and the human body must endure the entire timeline. That is why the most important question is not, can we get there, but can we endure the full cost of staying long enough to come back? Because if that answer is still uncertain, then this is not yet a truly round-trip journey. It is a commitment so long that it begins to resemble a temporary departure from Earth itself. And this is where a deeper truth begins to emerge. Not all limits appear as walls. Some appear as time. Time changes your body. Time wears down your mind. Time magnifies small errors. And in a Mars mission, time is not on the side of humans. It is on the side of orbital mechanics, on the side of the environment, on the side of what has always been true. Space does not adjust itself to fit us. We must adapt to it. And when that adaptation stretches across hundreds of days, thousands of hours, through cycles of low gravity, radiation, isolation, and waiting, the final question is no longer technical. It becomes human. How far can a person go before the journey itself begins to separate them from the place they once belonged? That is the question the next part must face. Because if orbit forces you to stay, then the next thing to understand is what that time is really doing to your body at the deepest level. For decades, scientists have been trying to answer a very specific question. What happens to the human body when it leaves Earth for a long enough time? This question did not begin with Mars. It began with missions in low Earth orbit, where humans could observe long-term changes in a microgravity environment. Data from the International Space Station shows that after just a few months, the human body begins to change in very measurable ways. Bone density decreases by about 1 to 1.5% per month in key load-bearing areas, such as the hips and spine. For comparison, on Earth, an older adult might lose about 1% of bone density per year due to natural aging. In space, that process happens nearly 10 times faster. After 6 months, an astronaut may lose up to 10% of bone density in certain regions. And if extended to a Mars mission lasting 2 to 3 years, models suggest that loss could exceed 30 to 40%. This is not just a number, it is a structural change. Bones no longer maintain the same strength. Their ability to tahammul load decreases. The risk of fractures increases, especially when returning to an environment with higher gravity. Muscles change in a similar way. Studies show that muscle mass can decrease by 10 to 20% within just a few months without strict exercise routines. Even with exercise, the decline still occurs, just more slowly. Muscle fibers begin to shift in structure. Endurance-based fibers gradually convert into less resilient types. This means the body is not only becoming weaker, it is also changing how it functions. The heart is not exempt from this process. In microgravity, the heart no longer needs to work against gravity to pump blood upward toward the brain. Its job becomes easier. And like any organ in the body, when it is no longer required to work as hard, it adapts. Heart muscle mass can decrease by around 10 to 20% during long-duration missions. Blood volume also decreases. Studies show that total blood volume can drop by about 10 to 15% after time in space. This does not cause major problems in microgravity, but when returning to Earth, it leads to a condition known as orthostatic intolerance. You stand up and feel dizzy. In some cases, you cannot remain upright for the first few minutes. This has been observed in many astronauts returning from the ISS, even after relatively short missions. But perhaps the most significant changes occur in the nervous system. In recent years, MRI studies have revealed that microgravity affects brain structure in multiple ways. Fluids in the brain, normally regulated by gravity, begin to redistribute. Some areas experience slight compression, while others expand. This phenomenon is associated with a condition known as SANS, Spaceflight-Associated Neuroocular Syndrome, which affects astronauts' vision. Some astronauts report changes in eyesight after long missions. Not immediate blurring, but a gradual adjustment that, in some cases, does not fully return to normal. In addition, studies on animals and cellular models suggest that cosmic radiation, combined with microgravity, may affect cognitive function, memory, concentration, processing speed. All may be impacted. These changes are not always obvious in the short term, but in a journey that lasts for years, they become a factor that cannot be ignored. And this is where everything begins to connect. What we have seen so far are not separate problems, not just radiation, not just microgravity, not just the Martian environment, but the combination of all these factors happening at the same time, inside the same body, over the same period. And the crucial point is this: the human body was not designed to handle that combination for extended durations. On Earth, if one system in the body is under stress, others can compensate. If you lose bone density due to aging, gravity still stimulates regeneration. If you experience stress, the natural environment provides pathways for recovery. In deep space, those support systems no longer exist in the same way. No gravity to stimulate bone, no natural cycles to regulate circadian rhythm, no protective layers to reduce radiation. Everything unfolds in a state where the body must self-adjust, without having the conditions needed to do so effectively. And this is where a difficult truth begins to emerge. You are not just adapting to a new environment, you are gradually becoming a different version of yourself, shaped by that environment. A body accustomed to lower gravity, a cardiovascular system functioning under different conditions, a skeletal structure no longer suited for Earth's pull, which leads to a very important question. When you return, do you truly come back the same? Physically, the answer is you can return. But biologically, the answer is far more complex. Some changes can recover. Muscle can be rebuilt. The cardiovascular system can readapt over time. But not everything returns to its original state. Bone density, in many cases, does not fully recover. Changes in the nervous system may persist. Radiation damage to DNA accumulates. And all of this happens while you are still continuing the journey. This is not a process you can pause. There is no point where the body can fully recover before moving on. No phase where everything returns to balance. The changes continue, from the moment you leave Earth until the moment you return, if you return. And when you look at the entire picture, something becomes clearer. The limitation of a Mars mission is not what we can build. It is how long the human body can remain stable while everything around it is pulling it away from that stability. This is not a problem that can be solved with a single piece of technology. There is no device that can fully replace gravity, no shield that can completely eliminate radiation, no system that can perfectly recreate Earth's environment for years. There are solutions that reduce risk, but none that remove it entirely. And so the question is no longer, can we go to Mars, but can we remain ourselves throughout the journey? And if the answer is not entirely, then every mission like this is not just a step forward into space. It is a step forward that comes with unavoidable changes to who we are. For many years, Mars was always spoken of as a distant goal, something that belonged to the future, with no clear sense of when it might actually happen. But by the mid-2020s, the way we talk about this planet has changed. It is no longer just an idea. It is becoming a plan. Elon Musk has accelerated this shift more than anyone else. He does not speak about Mars as a symbol, but as an engineering project that can be built step by step. At the center of that plan is the Starship system. This is not simply a larger rocket. It is designed as a complete transportation system, fully reusable, with the goal of reducing launch costs to levels never seen before. In its published designs, Starship is capable of carrying over 100 tons of payload in a single flight, or transporting dozens of people at once. That number matters, because building anything on Mars is not about a single mission. It is about hundreds of missions. You cannot create a living environment with one landing. You need to transport equipment, materials, energy systems, supplies, and people across multiple launches over many years. In long-term plans, the goal is not just to land on Mars, but to build a system that can sustain itself. A place where humans do not simply survive temporarily, but can exist over the long term. That is why the idea of a colony is often mentioned, though in reality, it is closer to an engineered ecosystem than a traditional settlement. Meanwhile, SpaceX's tests between 2023 and 2026 have made one thing clear. Launching and controlling a system of this scale is becoming increasingly possible. Test flights have reached important milestones, achieving orbital attempts, stage separation, and in some cases, controlled returns. There are still failures, but the direction is no longer uncertain. At the same time, NASA is not standing still. Instead of going directly to Mars, NASA is building a sequence of intermediate steps with the Artemis program at its core. The goal of Artemis is not just to return humans to the moon. It is to use the moon as a testing ground for technologies that will be required for deeper space missions. On the moon, distances are shorter, support is more accessible, and risks can be managed at a more acceptable level. It becomes a place to test life support systems, long-duration operations, and survival strategies in harsh environments before scaling them up for Mars. One of the most important areas of research is closed-loop systems. On Earth, you never have to think about recycling air or water. In space, it becomes essential. Current systems on the International Space Station can recycle about 90% of water, including humidity and waste. This is a major achievement, but it is not enough for a mission that lasts for years without resupply. Recent research aims to move toward nearly fully closed systems where all resources are continuously reused. In theory, this makes sense, but in practice, every closed loop introduces small errors, and over time, those errors accumulate. This is one of the reasons long-duration simulations on Earth are so important. NASA's CHAPEA program is a clear example. In this program, volunteers live in a Mars-like simulation for more than a year, in a confined space with limited resources and a schedule designed to mimic a real mission. The goal is not to test whether humans can survive. That is already known. The goal is to understand what happens when that state continues for a long time. After hundreds of days, when everything becomes familiar, when there is no novelty, when each day begins to feel almost identical, what begins to change? Early results show something remarkably consistent. It is not the workload that creates the greatest pressure, it is repetition. No changing environment, no natural signals to mark time, no unplanned interactions. Everything becomes structured to the point of monotony, and within a closed system, there is no way to step outside of it. While human research continues, robotic missions are still operating on Mars. The Perseverance rover is one of the clearest examples of how humanity is preparing for that future. It does not just collect soil and rock samples. It carries a device with a very specific purpose, MOXIE. This instrument is designed to convert carbon dioxide in the Martian atmosphere into oxygen. In its tests, MOXIE has been able to produce a few grams of oxygen per hour. That number is extremely small compared to human needs. An adult requires roughly 550 liters of oxygen per day to survive. But the significance of MOXIE is not its output. It is proof that the principle works. Moving from a small experimental device to a system capable of sustaining human life for years is a massive leap. But it is a leap scientists are actively working toward. Similarly, research into producing fuel directly on Mars using subsurface ice to generate hydrogen and oxygen is also advancing. The goal is to reduce dependence on Earth, because if every mission had to carry all the fuel required for both the journey out and the return, the mass would quickly become unmanageable. These developments reveal something important. Humanity is not just thinking about Mars. We are building the pieces needed to reach it. But when you step back and look at the full picture, a subtle detail becomes clear. Most of these technologies are still in transition. They work in experiments, they work at small scales, they work under controlled conditions, but none have yet been proven to operate continuously, without interruption, for years in the actual environment of Mars. This is not a flaw, it is the nature of technological progress, but it shows that the gap between possible and sustainable is still very large. And within that gap, the most important questions begin to emerge. Not about whether we can get there, but about what must happen for us to stay. Because when you look at everything being built, rockets, life support systems, long-term survival models, a clear direction appears. We are trying to bring a piece of Earth to a place that is not Earth. And every step forward, no matter how small, is part of that effort. But at the same time, every step forward also makes it clearer what has not yet been solved. The progress we've just discussed is real. Larger rockets, better systems, more successful tests each year. If you only look at that direction, it becomes easy to believe the story is almost complete. That with just a few more steps, humans will be able to live on Mars. But when scientists begin placing all of those advances into a single system, something else starts to appear. Not a lack of technology, but an overlap of limitations. A system can work well in a laboratory. A device can run reliably for a few hours. A model can be correct on paper. But when all of these must operate together in an unforgiving environment for years without interruption, the story changes. And this is where the question shifts. It is no longer, can it be done? It becomes, can it be sustained? One of the clearest challenges is reliability. On Earth, we are used to repair. If an electrical system fails, components can be replaced. If a water filter breaks, it can be fixed or swapped out. If a device stops working, you can call for help. On Mars, that concept barely exists in the way we understand it. Not because of a lack of skill, but because of a lack of conditions. The distance we discussed earlier is not just a communication problem. It is a logistical one. A critical part cannot be shipped in a few days. A technical team cannot arrive when needed. A mistake cannot be solved by simply calling for support. Everything must be anticipated. Everything must have redundancy. And every layer of redundancy increases the complexity of the system. This creates a loop. You add systems to increase safety. New systems introduce new risks. You add more systems to manage those risks. And over time, the entire structure becomes so complex that perfect control is no longer possible. This is not a new problem in engineering. But in an environment like Mars, where there is no natural buffer, every small deviation becomes more significant. A minor pressure imbalance, if not corrected, continues to accumulate. A small error in a recycling system may not cause immediate issues, but over days or weeks, it begins to affect the entire system. And because everything is interconnected, a small failure is rarely just small. It spreads, slowly but steadily. Another major factor is energy. On Earth, energy is almost invisible in daily life. You flip a switch, and it is there. On Mars, energy is the foundation of everything. Without energy, there is no artificial air, no clean water, no temperature control, no functioning systems at all. Current solutions primarily revolve around solar power and small-scale nuclear energy, but each comes with limitations. Solar power depends on sunlight, and sunlight on Mars is not stable, especially during dust storms that can last for months. Nuclear power is more stable, but it introduces complex requirements for safety, maintenance, and long-term management. And in an environment where replacement and repair are extremely difficult, every energy system must be designed for extraordinary reliability. This is where problems begin to stack. Life support systems require energy. Protective systems require energy. Thermal control systems require energy. And all of them must operate at the same time. There is no pause, no standby mode, no natural fallback. Then there is another factor, less often discussed: operational time. A system on Earth might be designed to run for a few years with scheduled maintenance. On Mars, that same system must run continuously for many years, without the same level of support. This changes how we define durability. It is no longer about whether something works, it is about whether it still works after tens of thousands of continuous hours. And even if a system achieves that level of performance, there is still another factor: humans. All of these systems do not exist in isolation. They exist to support people. And people are not perfectly stable systems. We have physical limits, we have psychological limits, we have responses that cannot be fully predicted. In engineering models, humans are often treated as part of the system. But in reality, humans are the least predictable element within it. Not because we are weak, but because we are complex. In an environment that lasts for years, where everything repeats, where small errors accumulate, and where there is no immediate way out, psychological stability becomes just as critical as any technical system. This is why studies like CHAPEA do not only measure physical health. They track behavior, emotions, and interactions between crew members. Because in a closed system, even a small change in behavior can affect the entire group. And when you put all of these factors together, something becomes clearer. There is no single problem, no single bottleneck that, once solved, makes everything easy. There are many factors, each manageable on its own. But when combined, they create a system whose complexity exceeds the sum of its parts. This is the true nature of the Mars problem. Not a single challenge, but a network of challenges interacting over time. And within that network, humans are not outside observers. We are part of it. An imperfect part, a part that changes. And that leads to a deeper question. If we must change in order to survive within this system, how far will that change go? This is not a hypothetical question. It is already being asked in serious research, not as should we, but as will we have to? If the environment cannot change fast enough, then humans may need to adapt more deeply, not just through training, not just through better equipment, but at the biological level. This opens an entirely different way of thinking. The journey to Mars is not only about bringing humans to another planet. It may be the first step in creating a version of humans suited for that environment. And if that happens, the question is no longer, can we live on Mars? It becomes, which version of humanity will live there? This is not a conclusion. It is a pause, a point where science and philosophy begin to overlap. Because at this boundary, numbers are no longer enough. Models are no longer enough. You begin to think about things that are harder to measure: identity, change, what we choose to keep, and what we are willing to lose. And perhaps that is what makes Mars different from every goal humanity has pursued before. It is not just a place to go, it is a test of how far we are willing to go, not only into space, but within ourselves. As everything begins to settle, there is a very simple way to look back at the entire story. No need for more theories, no need for more technology. Just place two planets side by side, Earth and Mars. On Earth, the gravity you are feeling right now is about 9.8 meters per second squared. It is not something you notice every day. You don't think about it when you stand up. You don't think about it when you walk. You don't think about it when you lie down. And yet, every movement you make depends on it. Your bones are built to carry that load. Your muscles function because of that force. Your cardiovascular system is optimized to work under those conditions. On Mars, gravity is only about 3.7 meters per second squared, roughly 38% of Earth's. That number does not create an immediate sensation, but over time, it changes how the body exists. On Earth, the air you are breathing contains about 21% oxygen. No equipment, no processing, no thought required. Every breath happens naturally. An atmospheric pressure of about 101 kilopascals allows that oxygen to enter your bloodstream efficiently, keeps water stable in liquid form and supports the entire biological system. On Mars, the atmosphere is mostly carbon dioxide, about 95%. Oxygen exists, but not at levels you can use directly. Pressure is only about 0.6% of Earth's. At that level, water is unstable, and breathing is no longer something natural. On Earth, a magnetic field creates a protective layer you cannot see. High-energy particles from the sun and deep space are deflected before reaching the surface. The thick atmosphere absorbs much of what remains. You do not feel this, but it is happening every second. On Mars, a global magnetic field barely exists. The atmosphere is too thin to provide effective shielding. The surface is directly exposed to radiation. There is no natural separation. On Earth, the average temperature is about 15 degrees Celsius. Not always comfortable, but within a range the human body can adapt to. Day and night follow a stable cycle. The sun rises, then sets. Your body adjusts to that rhythm. You sleep and wake. On Mars, the average temperature is about -63 degrees Celsius. The difference between day and night can reach tens of degrees. There are no large oceans to retain heat, no ecosystem to regulate the environment. Everything changes quickly and harshly. On Earth, water exists in liquid form on the surface. Rivers, lakes, oceans. You can see it, touch it, use it directly. Water is not just a resource, it is the foundation of life. On Mars, water mostly exists as ice, beneath the surface or at the poles. Under low-pressure conditions, liquid water is unstable. If it appears, it quickly evaporates or freezes, which means every source of water must be extracted and processed. On Earth, you are part of a complete ecosystem. Plants produce oxygen, microorganisms process waste, natural cycles keep everything in balance. You do not manage that system. It existed before you were born. On Mars, there is no ecosystem, no natural cycles. Every balance must be created by technology and maintained continuously. If you look at each factor individually, the differences are clear. But when you place them all together, something else appears. Earth does not just have one favorable condition, it has all of them at the same time. Appropriate gravity, breathable air, stable pressure, moderate temperature, a protective magnetic field, liquid water, a functioning ecosystem. None of these elements operate in isolation. They work together to create an environment where life can exist without constant effort. And that is the most important difference. Not distance, not technology, but the ability to support life. On Earth, you do not have to actively maintain your existence every second. You simply live. On Mars, every one of those conditions must be actively maintained. There is no pause, no natural support. You can think of it in a very simple way. On Earth, the environment works for you. On Mars, you work to maintain the environment. And when you look back at all of these differences, there is no need to add any conclusion. Just place the two planets side by side and observe. One place where everything is already set up to support life. Another where everything must be built and kept from collapsing. From another perspective, you could say, on Earth, life is the default state. On Mars, life is a condition that must be constantly maintained. And perhaps that is something we rarely notice, not because it is complex, but because it is so familiar. You stand up without thinking about gravity. You breathe without thinking about oxygen. You drink water without thinking about pressure. You sleep without thinking about temperature. Everything happens naturally. And when seen this way, no further explanation is needed. The difference is already clear. After everything we've just explored, Mars is still there, cold, distant, and unchanged. The plans to send humans there will likely continue. Technology will keep advancing, and perhaps one day we will truly set foot on its surface. But based on what science shows today, one thing has become quite clear. The human body was not designed to exist in that environment for long, without a cost. And once you begin to understand that, the way you see the place you are in starts to shift. Not as something ordinary, but as a finely balanced system, where every condition needed for life exists together, in a way we rarely notice. Tonight, you don't need to go anywhere. Just allow your body to return to its natural rhythm. Slow down, just a little, and rest in an environment where you truly belong.